Okay, so in this video, the first thing we're going to do is just talk about the basic ideas of distribution theory and what's cool about it. So I mean, we'll just go ahead and get started here. Um, so first of all, in differential equations and functional analysis, we often talk about equivalence classes of functions. So like we'll talk about like f or something. And basically what this equivalence class is saying is like f, is equivalent to g. If if f equals g almost everywhere. And this idea of saying two functions are equal or in the same equivalence class, if they're equal almost everywhere. This is an awesome idea. It's super useful. It's really helpful. So like basically what it's saying is, if we have a function that looks like this, and we have, its, cousin over here, these two functions are supposed to look the same, but let's say in this one we've got holes in the graph. We've got a hole up here, a hole down here, hole up here, things like that. But under this idea, we say that these two are the same, right? They're in the same equivalence class, so we can just treat them as the same, right? So this is a great idea, and we like this idea. So we'll kind of keep rolling with that. But there's one other little thing that you might notice, and maybe it's even obvious, right? Is we're saying that f is pretty much equal to g, right? But let's go ahead and let's say this right here is -1, right? So -1, so -1 and -1. But so if we plug in -1, right, what do we get in f? And f we get about +1, like we'll just say that's +1. And then g of -1 is equal to what? Well, g is about 2, right? 2. But 1 is not equal to 2, right? So we have kind of this weird situation in which, we're saying these functions are equal to each other, but then down here, it's like, well, we're plugging in some value, and the y values are not the same. So that it's just kind of a weird thing. So it's basically like here we've used this good idea, and we're saying, oh, okay, let's say two functions are equal if they're equal almost everywhere. But we really just need to take it the next step and say, we're running into problems when we evaluate this function. Now, given I'm choosing -1 as our x value because I know that's a problem point, whereas if you just threw a dart at this, they would be the exact same. But this ability to use a bad value and evaluate the function at these two, that's a problem. So what we do is we basically restrict ourselves and we say, all right, let's not evaluate these functions at any given points anymore. Let's just evaluate them in areas, right? So now, basically what we're saying is, let's, instead of being able to evaluate a function right at this -1, let's just evaluate it in a small interval, right? So just instead of -1, let's just evaluate it like right around -1, just like in this ball, right? And then this area here, right? And then if we evaluate it on that little interval, now, let's just call this interval around, let's call it a ball around -1. So now if we say f of, this ball around -1, and then g of the ball around -1, these two are actually the same, right? Given we do this little evaluation here in a certain way. So we'll get into that in more detail. But basically, the idea is, we like this equivalence class thing, and now in distribution theory, we're just taking it to the next step and saying, okay, we're sort of forgetting about almost nowhere points. But now once we remove our ability to evaluate everywhere, now we have really taken it the full distance that we want to take it, because we can't evaluate at a single point anymore. We can only evaluate on like intervals and things like that. So that's really the first key idea in distribution theory, and we'll kind of move on from there.